So if you go to problem 141 in the book, that's how we're going to work over this one. So pause the video and get to that problem so you can work through it. The equation that we're going to use is the same as on the other side, where we have negative Q is equal to delta T over the total resistance, based off of the delta T equals negative Q rec. And to find the temperature at any point, we're going to use the temperature initial, or delta T, minus the temperature at that point, or N, is equal to negative Q times the resistance total up to that point. So if you're looking for the second or third temperature, you're going to need the resistance equivalent of all of the resistances in between that point to find that temperature at that point. What that's going to give you is the temperature drop over each resistor as you go along. So for problem 141, we're given a problem where we have a heated body of water. There is convection heat exchange between a copper plate. There is conduction through the copper plate. Then there is convection heat exchange on the other end of the copper plate with a lower temperature liquid. So we're going to have three resistors. We have a temperature initial, converted to Kelvin. We have an H bar for the convection. We have a T1 at the initial boundary of the copper. We have the length and the K factor of the copper given. And we have a temperature 2 at the far boundary of the copper with a H bar given between that surface and the convection of the liquid on the other side with its final temperature. All of that's given in the problem. So L, it might say thickness, but that's L. There's no parameters given for surface area, so we just don't worry about it because all the surface areas just cancel out. We have our H bar 1, our H bar 2, our temperature initial, and our temperature 2, and our temperature final and temperature initial, and the K for copper. We have our thermal circuit that is temperature initial going into convection with our temperature first over our second resistor in conduction, with our temperature second at the other boundary with our last convection resistance, and our final temperature. To calculate our resistances, we come over here and we have our resistance total is equal to all of our resistances added together because we're in series. We have 1 over H bar 1, we have length over K, and 1 over H bar 2. And that gives us a value right here of 0.000567. And we have to find our delta T, which is going to be our initial temperature versus our final temperature, still in Kelvin. So that gives us a total of 59. You don't always have to convert to Kelvin for a lot of these problems, but it's always better to do it and get in the habit of it so that when you do get to a problem that you need it, you don't forget it and get the wrong answer. So now we use our negative Q is equal to delta T over our resistance equivalent, end up with the values plugged in, and we end up with a Q equals negative 104,137. Take that value and plug it into our temperature at any point equation. And since this problem is asking us for the temperature at the liquid boundary where the temperature drops down to 32 degrees, right here on the far side, we're trying to solve for T2, because that's already traveled through the first convection, through conduction, and is about to travel through the second convection. So we have temperature at T2 is going to be T2 is equal to our initial temperature, T naught, plus Q and the resistances through 1 and 2, or R12. So to calculate R12, we have the first convection and conduction, 1 over 2700 plus 0.02 over 375, gives us our resistance value. We have a negative value over here for Q, so it works out. We should have a temperature drop as we go from a higher to a lower temperature. So just a good check inside your system is if you're ending up with a higher temperature than where you started when it should be lower just by looking at the problem, you probably have a sign change or some wrong values. Come over here, we have T2 is equal to the initial temperature of 365 Kelvin plus Q of negative 104,137 times 0.000424. We end up with a temperature drop over those resistors of, you end up with the total temperature minus 0.44, or 444, giving you a temperature at temperature 2 of 302 degrees Kelvin, or 47 degrees Celsius. And so what that's telling us is that we're dropping over this resistive circuit to to 47 degrees Celsius before we have our exchange with our 32 degrees Celsius convection. Starting off at 92 degrees Celsius, so we have a 92 minus 37 degree temperature drop through the system before the second convection.